because the embedded processors have become incredibly powerful, we can run all these very sophisticated algorithms on them. And as a result, we can take images from a camera and we can detect an unbelievable range of things from them. And so it's the power of the microprocessor coupled with the right algorithms suddenly opens up an incredible range of things that we can do with just a very simple image sensor.
Hi, welcome to the Ojo-Yoshida Report Dig Deeper series. And this is a new series focused on embedded basics. We have a fabulous guest today, Jeff Bier, president of BDTI, engineering consulting company, but also he is founder of Edge AI and Vision Alliance. I'm going to give microphone to Jeff. Jeff, please explain yourself, who you are.
Thanks for having me, Junko. It's good to be with you. So I have been in the electronics industry and working in embedded systems since around 1990. Um, I started my career helping to design custom processing chips for medical imaging systems. And then later I started my own consulting company, BDTI, as the embedded digital signal processing industry was maturing and growing fast. And we worked in that embedded digital signal processing field for about 20 years. And then around 2010, we shifted our focus to embedded computer vision and machine learning. So BDTI today is an engineering consulting company working in embedded computer vision and machine learning. And we also started an industry partnership, as you mentioned, called the Edge AI and Vision Alliance, which is dedicated to really facilitating and accelerating the use of what I like to call machine perception, enabling machines to see and sense and understand the world around them so that they can be better. That might be safer, easier to use, more effective, more autonomous, more efficient, whatever the case may be. So today, I lead those two organizations, BDTI, the Engineering Consulting Organization, and the Edge AI and Vision Alliance, the industry partnership.
All right, very good. So, actually, part of the reason I really wanted to start this series is that I think industry really got ahead of itself by morphing embedded into so many different things. And as a marketer, probably that was right decision to call embedded more or less, put it in the bucket of IoT, and then more lately, embedded is thrown into the edge AI. But I want to go back to the basics, as I said. How do you define embedded? Tell me your own definition, Jeff.
Yeah, it's a great question. It's become almost a philosophical question, and it's something that I was just discussing with a colleague yesterday. It used to be, it's easier to understand, I think, if you rewind the clock maybe to 1990 or something like that. In that era, you had computers, right? We had personal computers, we had mainframes. Those were computers, and then we had embedded systems. An embedded system was typically a special purpose small computer that was embedded inside of something else. So, for example, if you had a VCR back in that era to record TV programs, inside the VCR, of course, was a tiny computer to do things like keep track of the date and time and your schedule of your programs that you wanted to record and that sort of thing. So at that time, I think we would have said, well, an embedded system, embedded computer is kind of a special purpose, dedicated purpose computer that's inside of something else, right? Inside a
Right.
car, piece of consumer electronics, piece of medical equipment, or what have you. But as the industry has evolved and as microprocessors have become ubiquitous, the lines are really blurring. So, for example, I recently needed to have a CT scan after I injured myself,
Oh
and
no.
the CT scanner has probably multiple computers in it, but the main computer that the operator interacts with, it's a lot like a PC, but
Ah,
it is integral to the CT scanner. So some people might argue like, well, that isn't an embedded system. It's basically a PC. It just happens to be bolted onto the side of that big CT scanner. Others would say, but it's integral to the CT scanner, so it's an embedded system. Eh, Reasonable people can disagree on
mhm,
these, but on these kind of where the boundary is. But I find it most useful to think about the definition of embedded as a computer that isn't a PC or laptop or server, a computer that's um, either integrated into another system or dedicated to some purpose. And sometimes it's really easy to see, like when I turn on my dishwasher, right? There's a tiny little computer in there that's controlling the cycles and the motors and pumps and so on. Others, you have to think about it a little bit. For example, if you imagine like a video surveillance system in a casino, there might be 500 cameras streaming video to
oh,
a machine room somewhere in the back of the building, which basically looks like a little data center, right? There's
right.
racks of computers there. Now, is that an embedded system? It's like debatable, but I would say yes, because even though it's not integrated physically inside of something else, it's integrated as part of a sort of purpose-built solution, in this case, a video surveillance system, and it has a dedicated
Yeah,
function. So if you subscribe to this very inclusive definition, then any kind of computer
yeah.
that isn't kind of a personal computer or a server is an embedded system. And so I prefer that very expansive definition, but reasonable people can differ.
That's a lot of ground to cover. Essentially, if it is not PCs, or if it is not smartphones, maybe, or if it is not data center, everything in between are embedded. Is that
Yeah,
correct?
I think so. And yeah, it's tremendous diversity of
Yeah,
applications,
yeah,
which makes it complicated to like generalize in any sensible way, right? We're talking about everything from a wristwatch that has a microprocessor in
yeah,
it to a even like city scale system. Like I talked about the casino
yeah.
application, but you can imagine like a whole city like London where they have thousands of video surveillance cameras feeding into recording and analytics systems. Okay, so we're talking about many orders of magnitude of scale from you know, the $1 processor that might be in the dishwasher to, for sure, millions, tens of millions of dollars of many processors that would go into a city scale dedicated system for surveillance or for traffic monitoring or some other application.
Yeah. Wow. But I think one of the things that embedded, well, maybe this is a lot narrower than what you just described, but I always thought that embedded is like, something, the device that's closer to people, places, and things. Is it not? I mean, that's kind of a debate.
I think
Yeah,
that's a fair definition. Or maybe another way to think about it that's related to that is a computer that we interact with not as a computer, right? We typically an embedded system, not always, but usually we're not using a mouse and a keyboard
right.
and
That's right.
a monitor. We're
Yeah,
interacting with it in other ways. For example, like when I set the cruise control on my car,
yeah,
right? I'm interacting with an embedded computer, but there's no keyboard, thank God, right? In the
yeah,
car, right? No keyboard, mouse, screen. It's just a
yeah,
few buttons and
yeah,
an indicator light or two on my instrument panel on
yeah.
the car. So I think that's also a useful way of thinking about its computer, that its main job is not to be a computer as we normally think
Mm,
of interacting with a computer,
right.
but it's got some other job. In this case, it's regulating the speed of the car.
Okay. So you touched upon a little bit before about microcontrollers or microprocessors. The purpose of this podcast series I'm envisioning is to look at embedded through a lot of different lenses, right? So I want us to go over the list of building blocks that are becoming increasingly important today's modern embedded systems. Let's go down the list because those are the elements that I want to cover with certain companies throughout the series. So the first one that comes to my mind is sensors. But what give me your list, Jeff.
Yeah, it's there are many. Right? First of all, there are the processors themselves, which
Yeah.
span tremendous, variety and range in scale in terms of cost, performance, power consumption, and kind of what features are integrated, what capabilities are integrated with the processor, from well under $1 for a processor that might run something like a microwave oven or a side view mirror in a car to thousands of dollars for a processor that might handle, let's say, multiple high definition video streams for some kind of, demanding industrial inspection application. So the processors are, in my mind, kind of the center of this web of components. The software running on the processor defines the behavior and capabilities of the system. And so even though we don't normally think of software as a component, the software is just as important, arguably more important than the processor in really defining. Processor is kind of a blank slate, right? Same
Right.
processor could run a microwave oven or a side view mirror of a car or wristwatch or a billion other things, depending on the software. So the software is critical, and
Yeah.
the building blocks and tools that enable creation of that software are critical. And that's, a whole big stack of things, compilers and development environments and development kits and software libraries and very long list of kind of software development tools and components. If we come back to the hardware,
Mm-hmm.
next to the processors, I usually think about maybe three classes of components that surround the processor. There's memory, of course,
Of course. Yeah.
to store program, to store data. There's various kinds of I/O capability, like these days it seems like almost everything's connected to the internet, right? Like my
Right.
my thermostat is connected to the internet, which allows it to know the weather, which is
Mm-hmm.
handy, and it allows it to send me a push notification on my phone when I need to change the air filter on my furnace. So that I/O capability, in this case, it's Wi-Fi
Yeah.
that allows the thermostat to connect to the internet, is another category of enabled by another category of components. And then the final one, arguably the most important one, which is the one you mentioned, is the sensors.
Mm-hmm.
More and more now, and this I think cell phones really led this charge in terms of making a multitude of sensors cost effective, right? Cell phones have an incredible variety of sensors, right? You've got compass, you've got motion sensors, you've got a microphone or possibly more, you've got cameras, multiple cameras of different types. You may have a version of a LiDAR in there for face authentication. You've got GPS, which is somewhere between a communication interface and a sensor, an incredible array of sensors, and this is becoming more and more common now. Like my thermostat that I mentioned that talks to the internet, well, it also has some kind of presence detector because when I walk by it, it knows I'm there, and that's when it turns the display on.
Oh,
Right? And of
I
course, it's a thermostat, so it's got to have a temperature sensor,
right.
and a humidity sensor is also very helpful, and it has some kind of user interface dials, buttons, and things so I can control it. So lots of sensors.
Yeah.
And back in the 1990s, a typical embedded system, like think about a VCR again, you'd have a numeric display, and you have just a bunch of push buttons and switches, and that's how you would program it.
Yeah.
These days, more and more, the reality is like my thermostat, it I don't have to tell it things. It learns things from sensors. It learns what the temperature is in my house. It learns if
Oh,
people are home. It learns well through the wireless connection. It learns what the weather is outside and actually what the weather forecast is going to be. So yeah, sensors would be I think the final and very important
wow.
um, sort of class of components. You've got the processor, all the software that runs on the processor, and all the tools and components that enable creating that software. And then around the processor, you've got memory of various kinds, you've got connectivity of various
Yeah,
kinds,
connectivity. Yeah,
like wireless connectivity, and you've got sensors
yeah,
of various kinds.
yeah. So, what are the challenges, though? The more I thought about this, I think back in old days, you mentioned the VCR, right? But whether it's a toaster or thermostat, these things, these embedded, classical embedded systems did only one thing or one task. But now I think people realizing because the processing power is becoming larger and larger, and sort of like they're throwing in more functions and features. Oh, we can do this and that. I mean, that is making things a lot more complicated than what embedded system used to be. No.
Absolutely, much more complicated, but I think also much more exciting, and a lot more value can
Mm,
be provided. I think an interesting way to see this is, I mentioned my consulting company, BDTI. We shifted our focus about 10 years ago to embedded computer vision. So let me just talk about computer vision for
sure.
1 minute. What we mean by computer vision is a particular kind of sensor, which is a camera, an image sensor, connected to a processor. And that processor is running software that allows the machine to interpret and understand some aspect of what's happening in the world through the images. So, a great example of this is if you have a recent model car, it probably has what's called in the industry lane departure warning or lane keeping assist, where if the car senses that you're drifting out of your lane unintentionally, it will either warn you,
Hmm.
or in some cases will nudge the steering to keep
Right.
you in your lane. And the way it's doing this is there are cameras in the side view mirrors that are looking down at the road, that are looking at the lane markings. That's pretty much the only way to detect lane markings because it's paint on pavement. So they're
Right.
cameras. So the cameras are taking pictures at maybe 30 frames per second. The pictures are coming into a processor. The processor is running algorithms that were designed to identify lane markings and then assess based on where the lane markings appear in those frames, where is the car in the lane and how is it trending? Is it more or less staying in the center of the lane, or is it starting to drift out of the lane? And oh, by the way, if it's starting to drift out of the lane, but the driver has activated the turn signal, then we're going to assume that's a deliberate lane change and we're not going to take any action. But if
Uh,
it's starting to drift out of the lane and the driver hasn't turned on the turn signal, then we're going to warn the driver, hey, by the way, looks like you're drifting out of your lane. Or in some cars, we're going to just actually tweak the steering a little bit to help keep the car
right.
in the lane. So why do I
Right.
bring this up as an example? The reason is that once you have a camera connected to a reasonably powerful microprocessor, you have what you can think of as a software defined sensor. What do I mean by that? What I mean by that is that that combination of camera plus processor can sense 100,000 different things. What do you want it to do? That's the code you
Oh,
write. That's the algorithm you run on it. You want it to detect lanes? It knows how to do that. You want it to detect pedestrians, people? Okay, you can make it do that. You want it to detect, um, let's say, turn it around and have the camera inside the car, to stick with the car example for a minute.
yep.
Detect that there's a driver in the car? Sure, no problem. Detect who that driver is. Is it a known person?
Mhm.
Sure. You want to have it detect whether there are passengers anywhere in the car? How many? Oh, is there a baby in the back seat? Wait a minute. Has everyone left the car, but the baby's still in the back seat? Okay, that's potentially a dangerous situation. We're gonna raise an alarm. What I'm trying to get to here is because the embedded processors have become incredibly powerful, we can run all these very sophisticated algorithms on them. And as a result, we can take images from a camera and we can detect an unbelievable range of things from them. And so it's the power of the microprocessor coupled with the right algorithms suddenly opens up an incredible range of things that we can do with just a very simple image sensor.
All right. So I want to actually cover two important elements of this modern embedded systems. One is, needless to say, artificial intelligence. And some of the examples you mentioned actually does use the AI algorithm. and also the connectivity part of it. I mean, I'm especially keen on the how to protect the security of the devices because it's connected. So let's go down the list from the AI side. What do you see as getting, you know, I'm just getting sick and tired of people talking about how the chat GPT is going to change the world. But before we get there, I think I want you to kind of explain what do you see, what's happening in AI world, including all the way to chat GPT.
Yeah, well, there's a lot happening, but I'm like you. I'm like more pragmatically minded. So like, show me the thing that people are in large numbers are willing to pay money for, right? As opposed to the like parlor trick,
Yeah,
right? Like ChatGPT itself is cool, but it's not clear that there's enough value there that typical consumers or businesses will pay money for it in scale. On the other hand, it can be the basis for products. People can build on top of it and build related things that clearly have super compelling value and that people and businesses will pay for. Where I see, AI is of course today deployed and used in many places, but since this podcast is about embedded systems, let's
right.
focus on that. Let's talk about, well, where is AI used in embedded systems
Exactly.
today? And the answer is, I think, a number of ways, but the most compelling way that AI is used in embedded systems today is in this uh, machine perception kind of usage, like I talked about a minute ago, which could use cameras
Yeah.
or other kinds of sensors, radar, lidar, time of flight sensors, sound sensors, vibration sensors, etc. What AI allows us to do in combination with embedded processors and sensors is get meaningful insights into what's happening in the world around that system. Great example. In the car, um, if you're driving your car, let's say you are a passenger in your car and I'm driving your car, and suddenly we pass from dry pavement to wet pavement. Will you be able to tell that by the sounds that the car is making? Yeah, you will. It's not a straightforward thing, but it's pretty reliable, right? You know the sound your car makes on wet pavement versus
Yeah.
the sound your car makes on dry pavement. Well, if you can sense that distinction, then an AI algorithm running on an embedded processor listening to what's going on in and around the car with a microphone, we'll be able to sense that distinction. And that's really useful information, right? For example, if you have some of this other safety technology, like forward collision avoidance using radar, it's really helpful to know whether the road is wet, right? Because stopping distance is going to be way, way longer on a
Yeah.
wet road. So the system should be more cautious, right, about warning or applying the brakes earlier in case of an accident. So this is the kind of thing, detecting the wet pavement through sound, that was really difficult before we could put
Mm,
AI in embedded systems. It could be done, but it was just very challenging. And what I mean by very challenging is they were the kinds of problems that often took hundreds or even thousands of person years of really bright people working on the algorithms to get them, because you need them to be reliable, right? It's not good enough for them to be right
right.
90% of the
Yeah.
time.
Yeah.
If it's a safety critical application, it's not even good enough for it to be right 99% of the time. It has to
Yeah.
be right 99.999 and some more nines
Mm,
percent of the time. And that's really hard because the real world is very varied, right? Like the environment of the real world that a car operates in is very different, very varied depending on the seasons of the year. Oh, this state or city uses a different material for paving than this one, so it sounds different. Or,
uh,
oh, this car owner put different brand of tires on their car, so it sounds different. So getting algorithms that are 99.99, etc., reliable with all this variability of the real world, it's really hard, or was, before the advent of practical deep neural network techniques, the
yeah.
modern era of AI. And now, if you can gather enough example data,
Hmm.
samples, to train a deep neural network, very often you can actually create an algorithm that will reliably detect
Yeah.
these things.
Yeah.
And that opens up an incredible world of possibilities of things that maybe we could have done in the past, but there was just prohibitively time consuming and costly to develop the solution. And now we have a much more direct route to develop a solution. And as a result, we're starting to see a huge proliferation of AI into all different kinds of products, including really inexpensive products like countertop kitchen appliances. And like I have a $30 consumer smart camera mounted over the front door of my house, and
Yeah.
it sends me alerts when people show up at the front of my house. Now I've had like 6 or 7 generations of different companies' smart home monitoring cameras.
Yeah.
Only in the last few years have we gotten to the stage where I don't get false alarms. With the earlier generations, I would get false alarms all the time for like, oh, it's windy and the tree branches are swaying in the wind, or a spider is building a web in front of the camera. And so it really it really degrades the utility of this kind of thing if you're constantly getting false alarms and having to look at the video clip and say, oh no, that's just tree branches. Oh no, that's just a truck driving by, a spider building a web. As of the last couple of years,
Yep.
I don't ever get false alarms. And that totally is a game changer in terms of the utility of
Yeah.
this product.
Yeah.
So AI coupled with sensors, and of course,
Yeah.
sensors are only useful out in the world to sense things, right? In the data
Right.
center, it's
Yeah.
not that helpful to have a whole bunch of sensors. There's not much happening, right? It's just big racks of computers. It's
Right.
out in our cars, in our homes,
Yeah.
etc., where the sensors are useful. So putting the processors close to the sensors, putting the right perception AI algorithms on them enables us to detect things reliably that where such that now we can deliver real value. For example, I can get alerts when someone shows up in front of my house and not be getting false alarms when it's some other random thing happening.
Right.
My car can know that the pavement is wet and can adjust its safety behavior accordingly. So this sensors, AI in embedded systems interpreting data from sensors, I think is the most important intersection
Mm.
between AI and embedded systems.
It's
It's not the only one, but I think to me it's the most important sort of commercially in terms of the size of the opportunity and also the impact wise, the impact that it's
yeah.
already having and that it will continue to have.
That's a good point. So it is really the extracting the insights, extracting important information out of things that are being sensed, right? And without AI, that becomes really arduous
Yeah, it's
task.
possible. It's been possible
Oh,
pre
yeah,
the current AI era, but just
yeah,
really difficult in many cases, and
yeah,
therefore most of the potential applications haven't been developed because companies couldn't justify the cost that
yeah.
required.
So tell me about the security issues, though. This has been heavily discussed when things started to get connected. When we talk about IoT devices and the modern embedded systems, as you pointed out earlier in this discussion, it's either there's definitely a connectivity in there, right, as part of the basic building block.
Yeah, I would say that prior to this emerging era of AI in embedded systems, the most significant change in embedded systems um, was the emergence of wireless connectivity as a ubiquitous capability. Right back in the 1980s and 1990s, when I started first tinkering as a hobbyist and then working in this field, um, the embedded systems were isolated things, right? Like taking that VCR example, it was a tiny computer inside the video recorder, tape recorder machine that had its
Mhm.
little job, but it didn't have any ability to communicate with the outside world except for a little numeric display and a bunch of push buttons and switches that you used to program it. So there's no way for it to know, for example, what the broadcaster's schedule was, or to get like a firmware upgrade to improve performance or correct bugs. It was just this isolated static thing.
Yeah,
Now, of course, and or I would say for at least the last 5 or 10 years, almost every system, embedded system, has some connectivity capability so that it can get information from the outside world through the internet
Can
can give
update it. Right.
information, right, can
Yeah.
get updates and so on.
Yeah.
And that really aids the utility tremendously. Think about like the vending machine that you find like in an airport or something like that, where it's got those old style like screw things that turn to push out the candy bar or whatever.
Yeah.
So, 20, 30 years ago, they were embedded systems, but they were completely isolated.
Yeah.
Now they're connected, and that's a game changer because now the company that maintains the machine can, for example, know when it's out of stock or running out of stock.
Right.
They can update the prices remotely. If it's got a display, they can, send advertisements that they use to promote certain products. And of course, they can upgrade and update the software.
Yeah.
So that's huge. And that's why I say that's an example of why I say that the emergence of internet connectivity has really been a tremendous uh, brought a tremendous transformation in embedded systems. It kind of really a big step up in terms of what these systems can do
It do.
and
Yeah.
how they can be managed and maintained and so on. And now with the emergence of AI in embedded systems, we're seeing kind of that another big wave of transformation and expansion in terms of the capabilities of embedded systems. Now, to your question about security, yeah, when you connect these things to the internet, you potentially open a vulnerability, right, for hackers to get in, and they do sometimes, and that can cause problems. I'm not a security expert,
Yeah.
but one of the things that I see is that often what people want to do to help with security is to consume the data in the device, the data, let's say, coming from the sensors, from the users
Mhm.
in the device, rather than sending the data over the
Ah.
internet. So a simple example of this would be, again, my home monitoring camera,
Right.
right? In the old days, 10 years ago,
Mhm.
the solution might have been to stream that video from the camera over my internet. In fact, at one point I mentioned I had like 6 or 8 different
Yeah.
generations of these cameras. At one point I had one that did that. It simply streamed the video over the internet to the server, the company that
Server.
that sold that
Okay.
product. Well, that's a little scary when you think about it, especially if you've got the camera inside your house, right? So here's a live video feed from inside my house going over
Ah.
the internet. That doesn't sound like the most secure
Yeah.
thing. Now, on the other hand, look at the current generation of cameras that I have. They do about 98% of their processing of the video in the camera. And what they do is video is only sent from the camera to the server to over the internet under two circumstances. Number one, oh, this is an event that you asked to be informed about.
Hmm.
We detected that event, and now we're sending you like a 10-second video clip to show you what's happening. Or number two, we're not really sure what's happening. Our intelligence in the camera can't really figure out this current situation. So we're going to bring in the big guns. We're going to send this clip up to our servers and let larger algorithms
To.
crunch on this so we get a more reliable result.
Mm.
Take this to the next step. If you have enough processing power and AI algorithms on the camera, I can tell my camera, you know what? Never send video up to the cloud if the people in the video are people in my family or other known people that I've told you about, right? So here's my family and other people known to me who are authorized to visit my house. And
Hmm.
I don't want alerts, or maybe I do want alerts, but I don't ever want video sent over the internet
Yeah.
when those people appear. I only want video sent over the internet when a stranger appears.
Yeah.
So now it's interestingly, you can see that the AI can actually help with privacy.
Right.
Combination of AI and the embedded processing can
Yeah.
help with privacy because the camera now doesn't need to send video potentially at all. Right? If,
Right.
if I wanted to design a product that never sent video but only sent alerts,
Yeah.
right? Oh, there's a person in front of your house. Okay. Now, if it's not sending video, I can't see what's happening, but at least I know there's a person in front of my house, and that would be a very secure kind of setup.
All right, we can keep talking, but I think this is a good way to wrap up in a way that I think I can see the progression or the more capabilities being added in a thoughtful manner to embedded systems. But Jeff, tell me about the conference that you are going to have in May and what's in it for us.
Yeah, so I mentioned this industry group that I lead, the Edge AI and Vision Alliance, and the Alliance runs a conference in May called the Embedded Vision Summit. It takes place in Silicon Valley in Santa Clara, California. And it's really the conference for people who want to build these kinds of systems that we've been talking about, these embedded devices
Mhm.
that use AI with sensors to enable systems and machines to understand what's happening around them. And once you then use that understanding to do a better job, whatever that might be more capable, more efficient, more autonomous, easier to use, or what have you. So the Embedded Vision Summit is in May, and it's a combination of a conference with both technical and business tracks and an exhibition where people can see a lot of the latest building block technologies like the embedded processors, the algorithms, the camera modules, the software tools, the ingredients that go into making these kinds of sensor intensive AI enabled embedded systems that we've been talking about. So,
Mhm.
for anyone interested in learning more about the underlying technologies, be that the hardware, the software, the algorithms, or the applications, the Embedded Vision Summit is a great way to do that.
Okay, very good. But I hear that you're going to give us some special code so that we can get discount on this.
Yes, any friend of Junko's is a friend of mine, and we have a discount code for listeners of the Ojo-Yoshida podcast. It's Summit 24 OYR for Ojo-Yoshida Report. So Summit 24 OYR. If you're registering for the Embedded Vision Summit, use that code to get a discount.
Very good. I'm looking forward to it. I'm planning to be there and talk to actual system companies who are using these building blocks and take the embedded to the next level. Anyway,
Wonderful. Look forward to seeing you there.
okay. Thank you so much. We'll talk soon.
Thanks for having me, Junko. Good to see
Bye.
you. Bye bye.